A working mathematician handed GPT-5.6 his own unsolved research, the kind of problem that takes experts years. What came back split the internet in half, and in the very same week, OpenAI claimed this exact model proved a 50-year-old conjecture in under an hour. One of those stories is a genuine breakthrough. The other is a warning. By the end of this video, you'll know exactly which is which, and whether AI can really do PhD-level math, or whether it just learned how to look like it can. Chapter 1. The Claim. Start with the hype, because the numbers are genuinely startling. There's a benchmark called FrontierMath, built by more than 60 mathematicians on purpose to be too hard for AI. In November of 2024, the best models scored under 2%. Under 2. By this month, GPT-5.6 Sol sits at 89% on the lower tiers. That is not an improvement. That is a different species. Then it got concrete. Since Christmas, 15 problems from the famous Erdos list, some of them open for decades, have moved from unsolved to solved. 11 of them credit an AI. And these are not vibes. Many were written up in Lean, a proof assistant that mechanically checks every single logical step, so the proof is either valid or it is rejected. No hand-waving. A Fields medalist, Timothy Gowers, one of the most respected living mathematicians, sat down with the model on an open number theory problem and watched it sharpen a weak bound into a strong one in under an hour. And then, the headline that set everything off. On July 10th, OpenAI published a proof of the cycle double cover conjecture, a problem mathematicians had chewed on since the 1970s, generated by the model in under 60 minutes. So it's settled, right? The machines can do research math. Not so fast. Because to trust any of this, you first have to understand how a chatbot proves a theorem at all. Chapter 2. The machine. Here is the part almost nobody explains. GPT-5.6 does not prove a theorem the way it writes an email. The flagship, called Sol, has a setting called Ultra Mode, and in Ultra Mode it does not think alone. It spawns a swarm of subagents, dozens of copies of itself, that split the problem, attack it from different angles in parallel, and then merge what survives. The cycle double cover proof used 64 of them at once. Think of it less like one lone genius and more like a room full of tireless graduate students who never sleep and never get bored. But raw searching is not the same as being right, and this is the crucial piece. The strongest results are written in Lean. In Lean, a proof is basically a program, and a computer checks that program line by line. If a single step does not follow, the whole thing fails. You cannot bluff it, you cannot hand-wave, and you cannot get partial credit. So when a Lean proof compiles, the math is genuinely correct, no matter which model wrote it. That combination, a subagent swarm plus a machine verifier, is the real engine. So what happens when you point it at a problem that isn't neatly packaged for a benchmark? Chapter 3. The real test. Enter a working mathematician who runs a channel testing every new model against the kind of problems he actually researches. Deep stuff, in a field called integrable systems, the sort of thing with names like nonlinear steepest descent and Fredholm determinants. He did not hand the model a clean benchmark question. He gave it his own research notes and asked it to combine his results into a new one. The first attempt was, in his words, a disappointment. The model produced pages and pages of writing, redefined the same symbols over and over, and buried the useful part under filler. Then it did something that made him laugh out loud. It added a proud little remark, pointing out that you can factor a constant out of a determinant. For anyone who has taken a first linear algebra class, that is a completely trivial fact, the kind of thing you would never write down, let alone highlight. He joked that if you put that in a thesis, you would embarrass yourself in front of your examiners. So round one seemed to confirm the skeptics. Impressive vocabulary, weak judgment, no real insight. Case closed. Except that is not where the story ends. because he did not give up, and what happened next is the part that actually matters. Chapter 4. The Turn. He changed one thing. Instead of dumping the whole messy problem on the model at once, he isolated the single hardest piece, the part he genuinely could not do by hand, and he used the model itself to help him write a sharper prompt. Then he switched to Sol Ultra, the subagent mode, and let the swarm run. This time it thought for far longer, and the answer that came back was, in his words, much higher quality, far more rigorous, with formulas that were genuinely interesting. It correctly identified the limiting object his problem reduces to, a Fredholm determinant, and it generalized the setup in a way he had assumed was true, but had never bothered to prove. Same model, same mathematician, night and day result. And that is the lesson hiding underneath all the hype. The bottleneck was not the intelligence. It was the framing, the mode, and knowing which question to ask. Which means the model did not replace the expert. It rewarded the expert who knew how to drive it. And that distinction is exactly what the loudest headlines keep leaving out. Chapter 5. The Asterisk. Now the asterisk, because the skeptics are not wrong either. Terence Tao, arguably the most famous mathematician alive, pointed out something uncomfortable. A lot of the problems the AI cracked were not hard so much as neglected. Nobody had ever seriously tried them. Solving a question that no expert bothered to attack is just not the same as beating one that defeated humans for decades, even if both look equally impressive in a headline. And it gets sharper. Some of the earliest claims that GPT had solved Erdos problems turned out to be false in a very specific way. The model had not reasoned out a new proof. It had found an existing published solution and repeated it back. That is not discovery. That is a very expensive search engine. And that 50-year-old conjecture proof, the crown jewel, it is being read in public by working mathematicians before any formal peer review. The cycle. Double cover conjecture already has a long graveyard of proposed proofs that looked right and later collapsed. So until independent experts sign off, the honest word is not proven. It is claimed. Which brings us to the only conclusion that actually holds up. So hold 3 things in your head at once. 1. The tool is real. When the answer is written in Lean and a computer verifies it, the math is correct. And that is a genuine, permanent step forward. 2. The hype is inflated. Repeating a published proof is not discovery. Solving a neglected problem is not the same as cracking a hard one, and claimed is not proven. 3. The human did not disappear. The mathematician who got garbage and the one who got a rigorous result were the same person, on the same model. The only difference was knowing which question to ask and being able to check the answer. So the question was never really, can AI do PhD math? The real question is whether it can do your math, and whether you are expert enough to tell when it is bluffing. Right now, the model is only as sharp as the person holding it. If this cut through the noise for you, subscribe. We break down what these models can really do, minus the hype. Next up, inside Lean, the language that lets a computer check a proof no human has the time to read. See you there.